Welcome back. Today we are going to look into exact values of trig ratios. We know what trig ratios are right now, which is sine, cos, and tan. And so at the beginning portion of this video, you don't need to write anything. You just need to listen and answer these following questions. So the first question here says, think about what was the first thing that you learned about right angle triangles before trig. So the first concept that you would have learned about right angle triangle should be a very famous theorem called Pythagoras' theorem. Now, the reason why we're going to look into Pythagoras' theorem is because there will be a certain concept, right, that occurs in Pythagoras' theorem, which can help us to understand and also find the exact values of trig ratios. Okay. So let's go into our second question. If we were to think back on the various questions that you have done for solving Pythagoras' theorem in year 8 and year 9, there are numbers that consistently come up. If you don't remember, that is fine. The first combination of numbers should be 3, 4, and 5, right? It's very famous. What it would look like on a right angle triangle would be 3, 4, and 5, right? 5 being the hypotenuse. Another one would be 5, 12, and 13, 6, 8, 10, and I think 8, 15, 17. Okay. So these, I guess, triplets of numbers, they will always come up. This is what we call really nice numbers. Okay. Now, the reason why we keep getting the same numbers over and over again, right? If you, let's say, were to go back to do Pythagoras' theorem, the reason why is because, let's say, I've got this length here as 3, and then my bottom or my base length of this triangle is 6, right? And I want to find, using Pythagoras' theorem, I want to find the hypotenuse. Let's call that x, right? Let's say I want to find that. To find that, I will go x squared equals to 6 squared plus 3 squared, right? 36 plus 9 should equal to 45 for me, right? So it'll be x squared equals to 45. How do I get rid of the squared? I would have to square root it. So my x would be square root of 45. Okay. So here, if I change it, this will be a square root of 45. See how now it's becoming not a nice number? What do we call this square root? We call this square root in third form, right? Thirds. Now, if we were to put that into the calculator, what we would have gotten is 6.708 and so on, right? Again, it's not nice. It's in decimals. It's yucky, So this is the reason why we keep getting the exact same numbers over and over again, because I would like my triangles and my lengths to be really nice and easy for me to solve. Now, this concept here is what is the same concept that we're going to use for trig ratios. But rather than it being the sides for trig ratios, we are going to look at it with angles. So there'll be really nice angles that we, I guess, use that will get us a really nice value. These three, right? These three nice angles are 30, 45, and 60 degrees. Okay. These three angles will give me a really nice value when I solve for it. Okay. So to test that, let's test using an example, sine 30, right? And let's put it into a calculator. If I put it into the calculator, I would have got 0.5, which in other words, if I put it into a fraction, a half, right? Now let's test it using SOHCAHTOA. Let's say I have drawn in my math book the length of 3 centimeters. And then I drew a length for my hypotenuse, 6 centimeters. Okay, and let's say from the base of that triangle that you made, the angle is 30 degrees. So let's use SOHCAHTOA, right? The opposite of my angle is called my opposite side. The opposite of my right angle is my hypotenuse, and my last side should be my adjacent. Okay. Let's that again, my adjacent. Okay. Now let's say I want to find sine 30. Okay, let's find sine 30. We know using SOHCAHTOA, sine is opposite over hypotenuse. So my opposite side, my value for that is 3 over 6. Right? If I were to simplify that even further, somewhat it's a magic, and I get a half. Right? So it works both ways. Now, using this, right, using what we know about sine 30, right, we know that using sine, it's opposite over hypotenuse. Now let's try and draw another right angle triangle, but using half, right, as our base. So again, I'm going to draw another right angle triangle. I'm going to label this angle right here at the corner, 30 degrees. Then my opposite side of that angle should be the value of 1, right? And the opposite of my the opposite of my right angle should be my hypotenuse, which is 2, okay? I'm just following the concept here, these type of values. Now, once I've gotten that, let's use Pythagoras to find the missing length, right? So let's use it. My hypotenuse is 2, so 2 squared equals to 1 squared plus b squared. Let's go b squared equal to then 2 squared minus 1 squared, right? 2 squared equals to 4 minus 1 squared, which is 1. 4 minus 1 should equal to 3. 3 equal to b squared. I'm just going to write it down here. How to get rid of the squared, super easy, you all should know. B should equal to square root of 3. So this should be the square root of 3. Now let's use that SOHCAHTOA, which we already know, right? This is the opposite side, this is the hypotenuse side, and this is my adjacent side. Okay, now we've got a really nice triangle with all its values and all its side lengths. So let's do this then, okay? Let's solve. Let's find what is cos 30. We know using SOHCAHTOA that cos is adjacent over hypotenuse. So let's just write it down. What's my adjacent in this triangle? My adjacent is square root of 3 all over my hypotenuse, which is 2. Super easy. I use my triangle to work out my exact value. Tan 30, let's use it. Tan using SOHCAHTOA, it's opposite over adjacent. So what's my opposite value? 1 over my adjacent value, which is square root of 3. Again, this is exact values, right? Exact values has something to do with square roots, right? That's what we call a special triangle. Okay, now on the exact same triangle, so if I were to draw it again, right, 30 degrees, this is 2, this is 1, and this is the square root of 3. There is actually another triangle from my nice angle. So if I were to just scroll back up, I have used 30 degrees. My other hidden angle, which is at the top right here, right, is actually 60, right, which is one of my nice angles. How did I get 60? Well, okay, this angle sum of a triangle is 180, right, and I got a 90-degree angle here. So that means these two angles must equal to 90, okay, which is what we call supplementary angles. So I'm just going to write it down here. 90 minus 30 degrees equals to 60 degrees, right? All these angles added up together. So the 90 degrees, the 60, and the 30 should add up to 180. Okay, let's use SOHCAHTOA then. I'm using now not the 30, but I'm using the 60 degrees. So the opposite of my 60 degrees is my opposite side, which is down here. My hypotenuse, the right angle stays the exact same. And now my adjacent is my 1. Let's find what's sine 60. Sine 60 is opposite over hypotenuse. So my opposite side is, or value is square root of 3 all over 2. Okay, let's see and compare. Doesn't this value kind of look exactly like this? Yes, it does. And the reason being is because 60 and 30 are what we call, not supplementary, complementary angles. Right? Complementary angles means that it adds up to 90. Okay, so if I were to find cos 60, right, rather than using this triangle, can I possibly use what I found here for sine 30? Let's double check. For sine 30, I got a half. For cos 60 on this triangle, I get, to no surprise, my adjacent is 1 over 2. Okay, again, because they're complementary angles, it adds up to 90. For tan 60, right, tan 60 is going to be opposite over adjacent. So my opposite is square root of 3 and my adjacent is 1, which is, of course, just square root of 3. Okay, we will talk about, I guess, the opposite of, or the complementary of the tan, but possibly not in this topic. Okay, maybe later further on. Okay, so I've used 2 of my 3 nice angles, so 30 and 60. Let's do my last one. My last one is the beautiful 45. 45 degrees is a very special angle. It's because it has its own complementary angle, right? Complementary angle equals to 90 degrees. Its own complementary angle is basically if I do 90 minus 45, I get 45 again, right? Makes sense. And so let's say I make another right angle triangle and I label my triangle as both sides here equals to 1, because if the angles are exactly the same, what type of triangles do I have? I would have an isosceles triangle, right? That's the reason why these sides here would be the exact same length. Then I need to find what my hypotenuse is, which is super easy. 1 squared plus 1 squared equals to 2. X squared equals to 2. I get x equals to square root of 2. Okay, let's just use it, right? Let's use one of the angles. If I use this angle here, this will be my opposite, right? This will be my hypotenuse, and this will be my adjacent. No matter which angle I use for 45, it'll still give me the exact same answer. Okay, so let's find sine 45. Sine 45 should be opposite over hypotenuse. So then my answer for sine 45 is 1 over square root of 2. Cos 45 would be adjacent over hypotenuse, which is, to no surprise, 1 over square root of 2. Again, it's their complementary angles. That's why it's exactly the same. For tan 45, it's opposite over adjacent, which is 1 over 1, which leads us to 1. Okay, that should end for our video today. I hope to see you guys soon. Bye.